Oh, hello, Dr. Akala.
Yeah, good morning.
Good morning. I see you've been very consistent with this training.
Well, it is new to me, but I want to see how much of it I can grab.
Yeah, Dr. Akala is one of the big professors at Howard University with a lot of research activity. That is why I want to acknowledge him.
Thank you.
Okay, so it's 11 o'clock and we need to start. I see people are now starting to log in or sign in, but time is of an essence, so we can start. And before we start, I have a few housekeeping things to do. But first, a good day, everyone, and welcome back to day 2 of module 4. So the next, module 8 is a series of research presentations on current topics. The next one will be Thursday from 11 a.m. to 12 noon. And the title of that presentation is a very lengthy one. I'm going to post it in the chat room. Is what you can learn about human gene expression when making 70,000 RNA sequence samples easy to use. The presenter is Dr. Jeff Lee from Johns Hopkins University. So you want to check your email next week for the invite to the research presentation. Also, today, the second day for module 4. So just please make sure that you complete the survey that will be posted in the chat area and also in Slack. So your feedback is very important to us, and then it makes us able to improve on this training. Before I hand over to Dr. Martin Skarzinski, we have a visitor here from NIH. That is Dr. Alisa Tillman. Dillman, not Tillman. Dr. Dillman was part of the planning committee for this program, VADSTI program here. She was very much involved from the beginning up to this point. She is the Workforce Development and Community Engagement Lead of the Office of Data Science Strategy at NIH. She has a word or two about a post-VADSTI program, so I'll hand over to Dr. Alisa Dillman to say a word or two on this, then we'll hand over to Martin.
Thank you so much.
Dr. Alisa, welcome and thank you for visiting us to grace this program this morning.
Thank you. And sorry, Martin, I didn't know it'd be specifically yours that I'm crashing. All right, I just had like 2 slides if I can share. Let's see if I can maybe do that. Uh-oh. Hopefully my computer doesn't crash. Oops. I have no idea what you're seeing.
We see your power.
We see it, yeah.
Okay.
Slide 4.
Too many slides back. All right, cool. All right. Sorry. So I just had a couple of quick things to say about, as mentioned, some things that will be going on after sort of the official part of the modules for VADSTI relating to cloud training and the Code-A-Thon. So just a, oops, why are you not? There we go. So I want to say a brief word about the cloud training. So the cloud training will be offered through the STRIDES program at NIH, and that's the the NIH Science and Technology Research Infrastructure for Discovery, Experimentation, and Sustainability. This initiative is basically a partnership with both AWS and Google Cloud service providers, and they offer a discount on using either AWS or GCP for any Strides initiative partner. So what that means is anybody who is NIH funded can opt into this program. This program also offers professional services. So if you have, if you're stuck on how to move something into the cloud, you can get in touch with the professional services team. There's also potential collaboration engagements as this program tries to connect other people that are doing similar work in the cloud. And then finally, obviously, the one that we're most interested today is going to be training. And that comes in a couple of different flavors. There's the structured training, which we're going to be offering in May. But then there's also in the works these sandboxes. So these cloud sandboxes will be access to either AWS or GCP for cloud testing. And that cloud testing could be things like shifting your training. So if you currently teach data science or bioinformatics, and you want to figure out how to move that onto a cloud-based system, you can utilize this sandbox. If you are a student who is currently doing analysis, bioinformatics or data science wise, you can actually use this sandbox to test how you would move your analysis and pipelines into the cloud. I have a form to fill out for those of you who are interested in the cloud training. So that way you can pick, so we have cloud training in both AWS and GCP. So if you could pick your preference and then pick which week in May you're interested in, and we will try to accommodate as many students as possible. What's the best place for that link on Slack? Which channel? Because there's like a whole bunch of different, maybe just the general channel would probably be fine. I can post it there.
What's in the module 4?
Okay.
All right.
And then the other thing we will be running is the Health Disparities Code-A-Thon. So that's NIH is partnering with Howard University to run this. It'll be June 21st through the 24th. The project pitches, the project pitch applications are not open yet. We're still working on the website, but they should be open by the end of March. And then the general participation applications will be in the beginning of May. This event is open to everyone, not just the VADSTI participants. So if you have friends who may not have been in this program, but would still be interested in a Health Disparities Code-A-Thon, let them know. We're partnering with Black in AI and Mechanism Design for Social Good, and they're going to be helping to serve as mentors for each team. So you'll have a lot of support. And then again, the Strides program and ODSS, so my office will be offering free access to GCP and AWS cloud computing as part of whatever it is that you're building in your team. So just to step back a little bit, so the project pitch, basically anything that relates to health disparities is of interest. So, you know, software, analysis, if you want to create training materials using health disparities data, you know, that's also a great project pitch. You can go through our list of previous projects so you can get a better idea of the kinds of projects that are in scope. You can actually pull previous projects and build on them so you don't have to come up with something completely on your own. If you have work that you're already doing and you're at a point where you're thinking, hey, having a couple more eyes on this would be useful, you know, that's a great place to pitch your project as well. And really the idea about a Code-A-Thon is to sort of, you know, be in teams with people you don't normally interact with and learn more about the tools that are currently being used from those people, you know, to promote public data sets when they're available in health disparities. And also, you know, the really great thing about this is the collaboration aspect. You know, we get to find really unique solutions for the problems that are of interest to our communities. So I will post the Code-A-Thon applications on the Slack channel as well when they open. All right, that's my little spiel. Does anybody have any questions or comments?
Yes, yes, just a quick inquiry. For some of us, we just signed on to this. So after the session, we may not have any link with Howard University. So if you post further information, I mean, how do we follow that up?
So we'll also have the announcement on the main, our main website. So I can put the website on the chat today.
I probably may not visit our university website, but probably you have our email. If maybe you have like an email list that you just shoot out an update and then upcoming information, that might be helpful, you know?
Okay, yeah. As
Yeah.
long as that works for the organizers, I think that works for us anyway.
Yeah.
And are you saying you just sign up for the VASTI program your first day?
I was not on for the first day. I think I
Okay.
came in the second week.
Okay. Yeah. So, Alison, yeah, you can do that too.
Okay, perfect.
All right.
Any other questions?
Okay, so if you don't have any questions now and then you want to send Dr. Dillman maybe a note in Slack, you can do that also. So now, Martin, I think you have up to 1:30 for your presentation. I think it shows on the distance 11 to 1, but it's actually 11 to 1:30. So it's all yours, Martin, and thank you for coming the second day.
All right, thanks so much. So I'm going to go ahead and share my screen. And today, the plan is that we're going to be doing more of kind of more practical work, right? So more hands-on, working with code more. But there's still maybe 2 more topics that I want to discuss. So last time we went up to, selecting the number of clusters using silhouette coefficient. We also talked about, basically looking at silhouette coefficient across clusters. So you can use silhouette coefficient to compare different numbers of clusters. So this would be different estimators. Okay, each estimator here has a different, each clustering algorithm here, or instance of a clustering algorithm, has a different number of clusters. Okay, and so here we're kind of comparing across models or across algorithm instances. And then here with this silhouette coefficient, what we're doing is we're looking kind of within the results of a single model instance, and we're looking at how well everything is clustered within for this one particular model instance. Okay, so this is kind of like zooming in on one of the particular points on this curve. Okay, so this would be comparing across models, and then here we're looking within a single model. Okay, so here this is k-means with k set to 3, right? As compared to maybe k-means with k set to 2, right? Okay, so that's what we finished off with last time. This time what I want to talk about is how we can understand our clusters. Okay? So, one way to do that is to use our cluster assignments as labels with some kind of supervised learning technique. So we talked about how there's, unsupervised and then supervised machine learning techniques. So with unsupervised, one example of unsupervised is clustering. Okay, so what we're doing, what we've been doing, yesterday, the whole time was just clustering, clustering, clustering. Now we're going to kind of build on that by including also a decision tree as part of our clustering work. So we bring in the decision tree after we already have our cluster assignments. Okay. So this decision tree is a supervised machine learning algorithm If it's for classification or regression, it works for both. But in this case, since we're working with cluster assignments and our cluster assignments, our cluster labels are discrete, we're going to want to use a decision tree classifier. Okay. So essentially, we're going to use these cluster labels generated by our clustering algorithm as the target for the decision tree classifier. Now, the purpose of this is so that we can understand our clustering results. So we want to infer what is the meaning of our clustering results. Okay. So first, what do? We instantiate, well, we import this decision tree classifier, we instantiate it, and I'm also importing this very handy function, this plot tree function, right? So here I'm setting up the data again. So this is redundant from before, but it's to make it so that this code is going to be able to kind of stand alone. So it's not dependent on previous code. Okay. All right. And so here we've got our data. We've imported everything we need. We instantiate our decision tree classifier. And then here I also put, random state equals 0. So that's just for reproducibility. I'm actually not sure if we absolutely need it, but I just added that in there. And then we're going to fit our decision tree classifier to all of our data, right? Now, so here what I'm doing is I'm not using the cluster labels yet. I want to show what it looks like when we do decision tree classification just on the data itself using the actual true labels. All right. Okay. The purpose of doing this is so I can plot the decision tree, and it'll show us basically the decisions that are used to create, to classify every single observation. All right. So this is what the decision tree does. Starting here at the top, all right, we're going to have our first decision. And the first decision is going to be petal width is less than or equal to 0.8. Okay. If we have, that being the case, then we say it's class Setosa. Right? Otherwise, we're going to kind of move in the other direction. Okay. And then we keep following these kind of binary splits until we finally have all of every single sample is classified. Okay. So this is how a decision tree works. Right. So we have, at each kind of decision point, at each branch point, we have a binary decision. It's going to be something like petal width is greater than 0.8. Petal width is less than 0.8. Here's less than 1.75. Okay. Here there's a decision that uses this sepal width. Okay. And then when we get down to these leaf nodes or these terminal nodes, right? We don't have any more decisions, right? We just have a certain number of samples that are already classified. All right. So this would be like a fully grown tree. We're going to have a certain number of samples. In some cases, the leaf only contains one sample. This leaf has 47 samples. And then also, because I passed in, these class name argument, okay, we also see what the class is. So these are the species of the flowers. So versicolor virginica, and then Setosa. Okay. So if we look at a plot, okay, we're going to be able to fairly easily see that Setosa is pretty easy to pick out. Okay. What's harder to distinguish is versicolor and virginica. Right. And I'll switch to the notebook code really quick, just to show an example of this. We'll go back to a previous plot that we already worked on. Okay, so over here, this one in green, okay, this is the actual, this is Setosa, right? And it's pretty easy to pick out. The other two are versicolor and virginica. Those are harder to distinguish, right? So you see, it only takes really one rule for us to kind of differentiate between Setosa and the other two. But for the other two iris flower species, we need many, many more rules. So this is a nice, very, very convenient function that we can plot out our decision tree. Okay? This part up here just basically sets the figure quality. So dots per inch, that's, you know, so I can zoom in and it still looks, you know, high quality. Okay. And the feature names, that tells us, you know, that's this kind of petal width, sepal width, right, petal length, and there's also sepal length, but, you know, the decision tree doesn't have to use all of the features. At each split, at each branch point, it uses whatever feature gives us the best separation. Okay. All right. So next up, what I'm going to do is I'm going to use a different type of clustering algorithm. I'm going to do agglomerative clustering, which we talked about. Right? So this is that kind of hierarchical clustering where we start with unique, you know, these terminal nodes or the leaves all have one single observation in them. Okay? And then what we start doing is we start combining the closest observations together, and we start kind of building up a tree until we get to the point where we're at the root node, which has all of the observations all in one cluster. Okay, so that's agglomerative clustering. It starts with everything in its own cluster. Each observation is in its own cluster, and then we kind of agglomerate everything together into one cluster. So that's the direction that it works. From the leaves up to the root of the tree. Okay. All right, and I use agglomerative clustering and hierarchical clustering kind of interchangeably. Okay, but in scikit-learn, this is called agglomerative clustering. Okay? So again, I import, and then I instantiate, and I can kind of combine the steps of fitting and predicting, okay, together with this fit predict method. So this gives me out my cluster labels. All right, then I'm going to start a new decision tree classifier, and I'm going to fit it to the data from before, but this time instead of the Y, instead of the label, right, instead of the true labels, I'm going to use the cluster labels. Okay? And this time, what I can do is I can get a decision tree that's going to basically tell me these, you know, these cluster labels, right? So then I can look and see how, kind of understand my, you know, how this is set up, right? And then one change probably that I should make is not use these iris target names because I think they're in a different order. But the point of this is to show how I can have, you know, some of these same splits, right? Let's say I didn't have the labels. This first split is exactly the same, okay, as what I had when I did have the labels. So here I'm not using the labels or the true labels, I'm using the cluster labels. But this first split is the same, and so I can kind of get the same information from it. And then I'll be able to say, okay, so this, so Gini is a impurity kind of index. It's like a score, it's a metric that's used. So the best way for me to show that is to actually look at here. where we have agglomerative clustering. We can do Shift Tab to bring up the documentation. And then search through here. There's going to be kind of for classification. So for clustering, it's going to be one of those kind of metrics that we can use. So here, affinity is Euclidean, right? And then for decision tree classifier, okay, so the criterion here is Gini. And this is this kind of Gini impurity index, right? So the other possible one that we can use for the decision tree classifier is entropy, okay? So this is how the decision tree decides where to split, okay? It's going to be trying to optimize this kind of Gini impurity index for a split. Okay, so great question. Thanks for that. Yeah. All right, so now I'm going to go here, and I realize that it's going to be much better. Yeah. Sorry, I couldn't hear. Someone trying to ask a question? Okay,
No,
I couldn't.
Martin, go ahead.
Okay, couldn't hear what that was. So if someone was asking a question, then you know, essentially, I'll say sorry, I couldn't, you know, couldn't figure it out. All right, so here, what's going on? I can kind of compare this decision tree, right, with the one that I had before, right? So first decision, right? If the petal width is less than 0.8, then the class is setosa. So I've got 50 observations here that are setosa. Okay, so that's very easy to classify. So this is with the true labels. Now going down here, this class 1, what is it? It's these same 50 labels. Right? The Gini impurity here in this decision tree. So this is pure, it's absolutely pure. So here we're done. This is a terminal you know, node, so it's a leaf, right? So this first class, this class 1, or you know, actually it's the second class, the one indexed by 1, is very easy to classify. Okay, so all we need is this one decision, and we can classify all 50 of the setosa flowers just based off of this one feature. Okay, and so based off of what we saw in the previous chart, we know that class 1 is setosa. Okay, if we didn't have any knowledge of the data set, we would call this class maybe the narrow petal class. All right, and so using this, we've learned something about our clusters, right? So actually this would be, you know, this cluster 1 is setosa, right? And our clustering results, our cluster labels here match really well our true labels. Okay, so when Gini is 0, this Gini impurity index, that means that it's absolutely pure. All 50 samples are class 1. Just like what we saw above here, where all 50 samples are setosa. Okay, so far, you know, this part where we're comparing our results with here the true labels and the results with the cluster labels, they matched perfectly. Okay, so we can put ourselves kind of in, you know, kind of a hypothetical situation where we don't have the true labels and we kind of have to be detectives, and we have to infer from just what we see what these clusters mean. Okay, so we would look at the feature and we'd say, okay, so this class 1, which we know actually is setosa, but this class 1 or cluster 1, right? We know it's going to have narrow petals. So petal width is going to be below 0.8. Okay, so and the units are centimeters, right? So we know that if the width of the petal is less than 0.8, then it's going to be this cluster 1 or class 1. Okay, so we already learned something about the setosa flowers, and also something about cluster 1, that it is defined by those flowers have narrow petals. Okay, and we can use this kind of approach to try to understand also the other clusters as well. All right, so here we're going to have 55 samples where it's class 0. All right, and then we can follow this as well. Okay, so if we have petal length less than or equal to 5.15, sepal length less than 6.45, we're going to have class 0 or cluster 0. Okay, so what it seems like is that class 2 is going to be, or this cluster 2 is going to have kind of longer petals and wider petals. Okay. Right. And that matches our here the results of that we plotted before. Okay, so that we're going to have basically this difference. So here it's not labeled, but it's petal length, petal width is what's being labeled, because our plot k-means function takes kind of the first 2 dimensions, and that's petal length and petal width. Okay. All right. So this is just an example of how we might go about, kind of understanding what's going on, learning something about our clusters. Okay. So cluster 1, narrow petals. Okay. Cluster 0, I would say would have, maybe more, let's say shorter petals than cluster 2. So this is something we can use as a tool to understand what's going on. So the next thing I want to talk about, that can also help us to visualize our clusters, understand our clusters, to know what's going on, is principal component analysis. Right? So principal component analysis is another unsupervised machine learning technique. So this also doesn't require us to have any kind of labels. So we would use this on our data, right? On our features. Okay, so that would be capital X in what we've prepared so far. Okay. And essentially what it does is it's going to find the combination of features that best linearly separate the data, right? Or kind of describe the most variance of the data, right? So here we're going to have something that's like X and Y, right? Or, let's say actually it would be like X1, X2. And then this red line is showing us that, this X1, X2, they're kind of can be combined together into this first principal component. Okay. Then perpendicular to the first principal component, so kind of at a 90-degree angle, we're going to have the second principal component. Okay. And so this is just a simple example of principal component analysis. So it's dimensionality reduction. We start with multiple dimensions, and then we reduce those dimensions down into a certain number of principal components. Okay. So here, this is another flashcard from Chris Albin, which shows how this can be used to take a certain number of dimensions and then reduce those dimensions down with only a small amount of information loss. All right, so that's PCA principal component analysis. Now with scikit-learn, we're going to import PCA, this PCA class, from the deep composition submodule. So up until now, we were using the cluster module. And from there, we used, agglomerative clustering. We used also k-means. Now we're using, and then also before from the tree module, we used the decision tree classifier and then also plot tree. So this PCA is coming from this decomposition module. Right? So we instantiate after importing and preparing the data. We instantiate our PCA, and then we fit it to our data, and then also kind of immediately afterwards transform our data. Okay, and this gives us this kind of what I call X sub R, right, or XR object. Here I'm setting up some kind of parameters for the plot that I'm going to make. And then I'm also kind of providing these values of how much variance in the data is explained by the first two principal components. Okay, so those are actually the only two that we fit, right? So the purpose of this, the reason why I'm running PCA is because I want to plot multiple dimensions, in this case 4, in two-dimensional space. Okay, so another thing that I do with my PCA model instance is that I'm going to pull out these kinds of loadings here from this components underscore attribute, right? And so it's going to be PC1 or principal component 1 and then principal component 2, all right? So I have this data frame here available, and these values for each of the features can kind of inform what the principal components are composed of, all right? And, this data frame is useful, but it's really much more helpful to look at this on a plot, okay? But the take-home message from this slide would be that, principal component 1, it's going to be kind of high in petal length, okay? And then maybe kind of have intermediate values in petal width and sepal length. Okay. Whereas principal component 2 is kind of high in sepal length, okay? And then has actually a negative value for petal length, right? So that's the kind of difference between these principal components. And you can see how we have 4 features now being combined into these 2 principal components. Okay, so here we're going to plot our very similar plots to what we did before, where we're going to have these 3 species, right? So these are the actual labels, and we're plotting this, kind of all 4 dimensions on a 2-dimensional plot, thanks to the fact that we're using this principal component analysis. So we've got principal component 1 and principal component 2, all right? So you can see how principal component 1 really separates out the data very well. Okay. So here we've got setosa. So from our decision tree, we saw that setosa has, much shorter, or it was much narrower petals, but also it's going to be much shorter petals as well, right? And so it's very easy to distinguish. Okay, so here's setosa. Okay. And then what's harder to distinguish is this versicolor and virginica species. All right. And these arrows, right, these are created from that data frame that I showed earlier. Okay. And so one thing that I can do is take a look at this data frame here, kind of off to the side. Oh, okay, I'm having trouble collapsing this sidebar. All right, I was going to try again. Nope, I think it's just not going to work. For some reason, it grabs on. I can't then let go. Okay, I did it. Okay, there we go. All right, so I'm going to have here on this side this data frame. So then we can look here at this plot on this side and understand what these arrows mean. Okay, so here I'm plotting, with the arrows, I'm plotting these kind of principal component loadings for each of the features. Okay, so for principal component 2, right, those are going to be, high in sepal length and sepal width. Okay, so here we've got sepal length and sepal width are these 2 arrows, okay, which are high in principal component 2 up here. All right, so if we look, the one that's higher, the higher arrow, right, which is going to be like 0.73 here, that's sepal width, and this one's going to be sepal length. Let me try to annotate this. So hope everyone can see this. I should probably change the color. Do something with better contrast. So how about blue? Okay, so this is going to be sepal. Width is the first arrow. And then sepal length is going to be this next arrow. Okay, so this principal component 2, doesn't separate out the data as well as principal component 1. So it's mostly principal component 1 that helps us to separate out the data. Okay, and so down here we've got kind of these overlapping arrows. There are 2 arrows. Right? The one with this kind of longest. The longest arrow, that's petal length. So here I'm going to switch to a different color. I'm going to do red. Okay, so it's going to be petal length. All right, and then here, this shorter one is petal width. Okay, so again, to kind of summarize where we're at, we've got our PCA plot. We have also the cluster, the actual labels, the true labels. So purple here is setosa, cyan is versicolor, orange is virginica. All right. In addition to this kind of PCA plot, we've got this quiver plot with these arrows that shows how each of our features contributes to each principal component. Okay, so PC2, principal component 2, is made up of sepal width and sepal length. Okay, and principal component 1 is made up mostly of petal length and petal width. Okay, so then we can say that, this setosa it's distinguished or characterized by having low petal width, low petal length, all right? So short and narrow petals, okay? And then here, versicolor and virginica it's harder to distinguish these. Versicolor is going to have kind of intermediate petal width, intermediate petal length, all right? And then virginica is going to have the, just generally speaking, the highest values for petal width and petal length, all right? So these are kind of the labels of these arrows here, okay? And again, what I'm starting with, just like with the decision tree, I'm starting with the actual labels, the true labels, all right? Okay. So, but let's now again pretend that we don't have the actual labels and that we're just doing clustering and we want to kind of understand our clustering results. So now I'm going to do the same exact thing. So I'm going to do PCA, okay, using the cluster labels. All right. And so what I've done, I've used the actual names, okay, of the flowers for the cluster labels. So basically, I've replaced the cluster labels with the actual names. All right. And the reason why I did this is just to make it easier to compare. Right. So let's say we didn't have the actual labels. Right. We can now compare our cluster labels, the ones that we created with clustering, and the actual labels. Right? And so we see if we didn't have these actual labels, our clustering results would get us pretty close. All right. So when we look at this kind of in this two-dimensional plot with these two principal components, where PC2 basically combines the two sepal features, and PC1 essentially combines the two petal features, right? We can see it's very logical. Here, this cluster doesn't really overlap, right? So the virginica cluster doesn't overlap with the versicolor cluster. Okay. And we can also use this kind of quiver plot to try to understand what do the principal components mean, and then how do these kind of principal components help us to distinguish between the classes or the clusters that we're getting from our clustering algorithm. All right. So here I'm using the clustering labels from agglomerative clustering. All right. Now, we know, because we have the true labels, we know that there's some, it isn't perfect. Okay? You can look here at the actual labels, that all of these flowers here are actually being misclassified with our clustering label, if we just used our clustering label. Okay. All right. But in a sense, that's something that I think is maybe unavoidable, because with the 4 dimensions that we have, we can't we perfectly separate out these separate out versicolor and virginica flowers. All right. Okay. So are there any questions about this plot, what it means, how it helps us understand our clusters? Okay. The PCA plot and then the quiver plot, which is on top of it.
Martin, I think I have a question. So the vectors are orthogonal, correct? That we're showing, they just don't appear orthogonal, right?
So this is something that's separate from what was shown on that flashcard. The flashcard shows the principal components are are indeed orthogonal, right? But what we're showing here is kind of these individual features and their correlations with the principal components. Okay, so an ideal correlation, if a feature was synonymous with a principal component, it would go out to 1 on a principal component, right?
Right.
Yeah, but that wouldn't happen unless the principal component solely used that feature, and then everything else would be kind of like orthogonal to it, right? But this kind of shows what the composition of the principal components is, right? But simply these
So those are
values here that
eigenvectors, correct?
yeah, so I would just refer to them as kind of the correlations between principal components and
Okay.
the features. Yeah.
Yeah, I think I'm still not exactly clear though how the arrows are representing what the relationship between the arrows and the actual labels are from the graph. I think I understand it from the table format, from the data frame, but from the arrows connecting to the actual labels in the picture, I'm not quite getting that.
Yeah. All right. So that's great. We should definitely kind of talk about that a little bit more. So what I did before is I kind of annotated these, and here I'm gonna maybe do that again. So here, this one that's the highest in PC2 at sepal width.
Right.
Okay. And so what does that tell us? Well, so this one here, Virginica, what is it kind of characterized by, at least in terms of our clustering results, right? Well, it's going to be high, just in general, in sepal width. It's also going to be high in sepal length, right?
Right.
So here, I'm going to put it here. Right? Okay, that's good. And also, it's going to be high in these other two. So petal length and petal width, which kind of go in the same they're kind of overlapping here, right? So when we kind of combine these together, what we would describe Virginica as is it's high in PC2 and it's high in PC1. All right. And then what we describe versicolor as, right, is it's going to have either kind of, maybe just in general, it has more intermediate values for both, whereas some flowers have, very low values for sepal width and sepal length. Okay. So the other thing that I can say is that here, when I look at this, right, I see that for PC2, for principal component 2, these highest correlations here, right, sepal length and sepal width, that tells me that principal component 2 is made up, primarily of sepal width and sepal length, right? With principal component 1, it's made up mostly of petal length and petal width. So you can imagine that if we had something, that first principal component is going to give us kind of a line through petal length and petal width, right? And then principal component 2 is kind of going to go through that line kind of in 4-dimensional space, where it's going to be, then kind of characterized by sepal width and sepal length.
Yeah, see, I think I get that part. I'm still a little unclear. I feel like I could have done that interpretation without the arrows or the vectors there. And that's why I'm trying to figure out like what the value add of the vectors are.
Yeah. So
On the
these on the plot. So I think it's just to visualize essentially the data that's here in this table. And we just have 4 features. I think if we had more features, then it might be more helpful. Also,
Okay.
I think it's easy to pick this up from the table. because basically goes, petals, all the petal features are in principal component 1, all the sepal features are in principal component 2, right? So that makes it easy. But if we had more features and if it was more complicated, right, then maybe these quivers would be more helpful.
Got it. Okay.
But it's a perfectly valid point to say, maybe this is not that useful, right? Maybe the quivers are not that useful. And in this case, we just would look at the table and just say, aha, all right, so principal component 2 looks like it's made up, it has high values, right, for sepal length and sepal width, because there's this positive correlation. As principal component 2 goes up, sepal length and sepal width go up. Okay? And then principal component 1, okay, it has high values for petal length and petal width. So as these go up, so does principal component 1. Okay.
No, that makes sense. And in fact, it made what you said, if we had extra dimensions, I see how it could get much more complex then. So that makes sense what you just said about the quivers. So thank you. Yeah,
that's great. So what I've done this before is I've done this with kind of genetic data. And there, you'd have kind of these kind of quivers or these vectors, these arrows pointing in many different directions. And then they would be like variant names or some kind of, a change, a nucleotide change in a gene. And there it's kind of harder to visually parse those out. But we can then say, for example, we have like a cluster of patients. We'll say, okay, looks like these, kind of this direction on our PCA plot is characterized by, having, they're going to be kind of low in a certain variant, or they're going to be, have like a high representation of that variant in this kind of subpopulation. So that's what I've used it for. And as for whether putting the arrows on the plot, whether it's helpful or not, I think it maybe helps us to illustrate like this concept of understanding this. But if I were going to show this maybe outside of a class, what I might do is kind of put a circle around this cluster and explain what it is, right? And then, here in orange, we can write what does this cluster represent without putting the arrows, and it would probably be less confusing, right? Yeah, so we can just state what does principal component 1, what is it kind of characterized by?
Right.
Yeah.
Okay.
That's a great question. Thank you. Yeah, you're welcome. All right. So next up, what I'd want to do is, take a look at the exercises and, maybe answer any questions about the exercises. Okay. But, right now it's noon, so let's take a 10-minute break. Okay. So I'll start a timer. Okay, so this is kind of the end of the didactic material that I have. And, so maybe just I'll do a quick review before. So the decision tree, the purpose of that is that we can look at the decisions used to arrive at the classes that we have. And then we can look at these decisions and kind of understand, okay, so, let me actually switch to this, the code, okay? So we can look here and say, okay, so we know that cluster 1 is characterized by low petal width, okay? So this is kind of the defining feature based off of this decision tree. So we can understand, what does cluster 1 mean? Cluster 1 is characterized by flowers, or is kind of comprised of flowers that have low petal width, okay? So this is something we can get out from a decision tree. We basically just use a decision tree where we're using cluster labels instead of actual labels, right? And down here with PCA, we take our data that we used for clustering and we transform it, okay, using PCA. And the thing that I'm looking here is through the documentation. Okay, so attributes, right? And then here examples. So here it's doing fit. Okay. So there's documentation kind of examples at the bottom of each of these. Right? So we fit and then we transform. And then we can pull out kind of these components. In the documentation, we can read more about, that specific attribute. So that kind of components underscore attribute. Okay. So here, principal axes in feature space representing directions of the maximum variance in the data. So that's this components that I'm pulling out. And in order to create this data frame, and then also I'm using that to create this kind of quiver plot. All right. But at high level, this plot, what it's for is so we can visualize our clusters. We can use all of the dimensions that we use for clustering. We're going to kind of include those as these two principal components. So we can plot, multiple dimensions in two-dimensional space, right? And then I can also try to understand what the principal components mean by using this quiver plot, okay? So that's what we just went over. All right. So next up, what I want to do is, we'll take a 10-minute break. Then we're going to shift to working on the exercises. All right. So if you have any questions during the break, please let me know. Otherwise, we'll just pick back up in 10 minutes, which is going to be more or less, 10, 11, or 10 minutes, or 11 minutes past 10. If someone's asking a question, I can't make it out at all.
Yeah, hi all. As you are taking this short break, you can also use the time to complete the evaluation survey. I've posted the link in the chat area. I think you should also find that in Slack. So please, as you are waiting, use the time to complete the survey. Thank you.
I just wanted to mention that in addition to the survey, if you haven't had a chance to work on the exercises, you can use this time to get started. So I'm going to start going over the exercises after the break. Okay, so welcome back from the break. What I want to do now is to jump into the exercises. I'm wondering if there's a way I can collapse this sidebar. I think maybe if I click here, though I'm afraid to. No, that was the wrong choice. Okay. I'm absolutely unsure of how to collapse this. If someone knows, let me know in the chat. Okay, so I'm going to scroll down to try to make it smaller though. Okay, so that at least worked. Okay, so we'll look at the exercises now. We'll go through the exercises. All right, so first up, what I want to do is I want to explain a little bit about this digits data set because the exercises explain it in text, but I think it's maybe a little bit hard to understand. Okay. So what I'd want to do, there's a book called Python Data Science Handbook. Okay. And in that Python Data Science Handbook, I'll share the link in a second. Okay. So we can open up the book in lots of different places. We can read the book online, kind of an HTML version. So this is a fully, it's absolutely free. The book is, is online. And so there's a machine learning section. So kind of like, what is machine learning? Right, so it talks about the categories of machine learning, classification, right, regression, which we've already discussed, right? Clustering. All right. And so I'll share this link, and dimensionality reduction. Well, it looks like I've got, so there's some other things in the chat that I maybe missed. The values are what? Okay, so that's going to be something that's explained in this plot tree documentation. So if we look up plot tree sklearn. All right. So here, understanding the decision tree structure. So here you've got the values. So I'll provide the link to that as well. Okay. And then difference between Pca and cluster. Okay, so great. That's a great question. All right. So with clustering, we've got, rows, and we want to combine those rows, the rows that are most similar, we want to kind of put them into clusters together. All right. And then it's not, maybe not exactly the same thing, with the columns when we're talking about PCA, but essentially what it's doing is it's going to, each principal component will be kind of consist of several columns, okay? So the way that I would explain PCA, so that's dimensionality reduction, is we're combining columns, or we're combining features together, right? Whereas clustering, we're combining rows together, we're combining observations together into clusters, right? Okay. Okay, so transform data, yeah, you can mean center. So basically you're gonna subtract the mean from all the observations. What we're gonna do in the exercises is we're gonna scale. So we're gonna use the scale function from scikit-learn, which is, scaling, not centering. Basically, centering, you subtract, let's say, the mean to mean center. So you subtract some value. With scaling, you're going to do some kind of transformation that involves, kind of multiplication or division, right? Okay. So here, this is, this explains really well what the this kind of plot tree function that we get from scikit-learn. Okay. All right. So going back here to this link that I shared, this Python Data Science Handbook. Okay. So it talks about also dimensionality reduction. All right. So maybe just a quick recap. So classification and regression, that's supervised learning where we have labels, and clustering and dimensionality reduction, that's unsupervised learning where we don't have labels or we don't use labels. Okay. So here's this kind of high-level overview: supervised learning, classification, regression; unsupervised learning, clustering, dimensionality reduction. And we've done everything except for regression. So for classification, we did a decision tree. For clustering, we did k-means and agglomerative clustering in the code. We also talked about dbScan and mean shift. All right. For dimensionality reduction, we did Pca. So here in this next section, it shows this iris data set. Okay, so here's a scatter plot matrix of the iris data set, and you see these familiar features. So petal width, petal length, sepal width, sepal length. Okay. All right. And so this X that we've been working with, it's essentially, it's a feature matrix. So it's going to have n features, n samples. These are samples are observations, features, you can call those attributes or variables. And then our Y, these are going to be, with the iris data set, these are the species, it's a vector. Okay. All right. And then I'm going to kind of scroll through these things. So here's PCA. I would say looks similar to our PCA, where we have Setosa, and then versicolor and virginica. All right. And then with clustering, right, there's also a clustering example. And then the very next thing that comes up in this book, right, is working with the digits data set. So I'll share the link to this specific part. Right. Right above that location is also where you have your cluster. Okay, so here it's going to be using this Gaussian mixture model for clustering, or GMM, right? Just a different algorithm than what we used. Right? And then it's plotting here these different clusters, and you can see how there's some mistakes being made along the border of versicolor and virginica, right? Where some versicolor flowers are being being clustered with virginica. Okay. And so here, this is, I think, a good example of one cluster that's easy to, or one kind of species that's easy to differentiate, and the other two are harder, okay, to distinguish. Right? Okay, so right above this digits example, there's the iris example of clustering. Okay, but here this part really shows really well this digits data set. So what is this digits data set? Well, we're going to have these images, which are 64 pixels by 64 pixels, so square images of handwritten digits. And what we need to do is we need to classify these as whatever digit, right? So let's say, 0, 1, 2, 3, and so on, right? And you can see how some of these are pretty easy to classify, or we at least we can look at it and we can see, okay, I understand what that is. Other times it may be very difficult, okay, to distinguish like what exactly is this supposed to be. All right, these are handwritten digits. Okay, and the story of this data set, it's kind of also known as like MNIST data set, is that it was actually used by the post office to automate, understanding kind of addresses and zip codes and so on. Okay, so we want to be able to, kind of have an image of something written by hand, and then to understand what are the numbers that are being written. Okay. All right. So I'll skip this one. I'll go to classification of the digits. And this one here, what it's being shown is it's a confusion matrix of this kind of like 0, 1, 2, 3 these are the true values. And then here there are the predicted values. What this confusion matrix tells us is where the most mistakes are being made by this classification algorithm. Okay, the one here, it's called the Gaussian naive Bayes model, right? So here we see that the highest number of mistakes is when the true value is 2, but the model is predicting 8. Okay, so it's hard to distinguish 2 and 8. Right, that's where the most mistakes are happening. Okay, so this confusion matrix, that's what it tells us. And then here we can look at some examples of misclassification. All right, so this is kind of similar to what we saw before, except now we'll see what's correctly classified. Like, for example, this 6 is correctly classified. And then this looks like a 1 to me, but it's misclassified as an 8. Okay, similar with this is a 9, but it's misclassified as an 8. All right. Okay, so this is classification of the digits data set, right? Okay, so that's the data set that we're going to be working with. And the reason I shared this link is to kind of explain a little bit more about this data set, what it looks like, what is it useful for, okay? And then, kind of to expand on the text that's provided here. Okay. Well, actually, no, sorry, it's 8 by 8, so 8 pixels by 8 pixels, so it's 64 pixels total. That's what I think it is, right? Okay, so we've got 64 columns. Those are the pixels. Yeah. So in health, could this be used in differential diagnosis? Yeah, classification. So really, the things that we're working with here, you can use it for pretty much anything. And I'll show an example of something else that we can work with. So from scikit-learn.datasets, import load breast cancer. Okay, and this is a data set that we can use for classification. So we can use this as an example. So we'll have load load breast cancer. So this is a function, and then I'm going to just call it BC. So I'm going to load in this data, right? And then what we can do is we can do shift tab here to look at some of the information, right? Okay. So here we're going to have different things available, right? So I think this bunch works the same way as a dictionary. So I'm going to try to access keys. Yeah. So we've got, the data, the target, okay, target names. So let's look at here the target names. Okay. right? So malignant and benign. So in this data set, this breast cancer data set, we can use, we can try to classify malignant and benign. So that's an exact kind of example of what you're talking about, Stephanie. So you're absolutely right. We can get these, target names. Here we see we can do binary classification as malignant or benign. Okay, so maybe after we go through this example with the digits data set, we can really do the same thing with the breast cancer data set. I think it's going to be pretty easy to just kind of swap this out. And then here we're loading in the digits data set from this URL. But I believe that we can also load digits, here using scikit-learn. Okay, so load digits. So if I do this again, we'll be able to here do, I'm going to call it, let's call it digits, right? And then I'll do load digits. I'll do the function call. And so in digits, we're going to have a bunch of things. One of those things is going to be a description, which is this desker, short for description. And we can print this out, and we'll have a description of this digits data set. All right. Okay. All right, so maybe what I'll do is I'll combine some of these cells and I'll share some of the code that I have right now. Okay, so we'll return to these data sets if there's time. I just wanted to show how there are kind of these different options. And just similarly, we can have print out the description of that breast cancer data set. And so these same techniques that we're doing, we can apply them to, really any of these data sets, including this kind of breast cancer data set that's built into scikit-learn. Okay. All right. So the reason why we work with the iris data set, it's pretty simple. It has 4 columns, 150 observations. So basically 150 by 4 is the shape, and has 3 classes. So it's a fairly simple data set to work with. This breast cancer data set, it's going to have 30 columns or attributes, and then 569 rows or instances. Okay? So it's a little bit more complex, but we can do the same things that we were doing. So we can also cluster here and see whether our clusters match the actual classes which are provided, right? So that one's going to be here, this class is malignant or benign. Right? So we can, cluster, then we can visualize our clusters, see if our clusters match the true labels. We can also do a decision tree to try to understand how do the features kind of guide us to which how each observation is clustered or classified. Right? Okay. All right, but let's go ahead and work on the exercises. So the first thing that we're going to do here for exercise 1 is we're supposed to load in the digits data set, right? Using this URL. So of course I did that very easily here using this load digits function that's provided by scikit-learn. But I'm going to kind of follow the instructions in the exercise and then use this actual URL. Right? So one thing that we can do is we can open up this URL, and then it should, kind of either download the data set or show us the data set, but looks like it closed immediately on my computer. What I can do is I can take this URL. So here I'm going to run this code. I can take this URL and I can use some kind of shellcode to download it. So maybe curl the URL. Okay. Oops. All right. So, oh yeah, sorry. So I have to do, let's maybe try it without using this variable. So here I'll have to, and then I'm going to output it as digits.csv. Okay. So I've downloaded it, and then I'll have it, I believe, in my file system, which, to be honest, I'm not exactly sure what I did with it, how I broke it, but I'll have it kind of locally as well. Here's digits.csv. All right, so let me share this code. So this is just a way that I can. Here's some things in the chat. The data set said 64 attributes, so potentially 64 branches in the decision tree. The decision tree doesn't have to use all of the attributes, and then sometimes it'll use the same attribute multiple times. Okay, so there's really no limit to how many branches we can use, to fully grow out the tree until all of the observations are in the terminal nodes. Okay, so if a tree doesn't have any kind of stopping criteria, it'll keep growing until everything is pure. All right, and it doesn't necessarily have to use, all of the attributes, doesn't have to use all of the features, right? And it can use some features multiple times. All right, so here, the shortcut key to combine cells, which is what I used here, is Shift M. So it's, let me maybe create an example here. So I'm pressing B to create a bunch of cells, right? And this one's going to be 1, 2, 3, 4. So here are a bunch of cells. And then I'm going to hold Shift and press M to combine these cells together. Okay. And then if I want to split the cells, I'm going to do Control Shift minus. Okay. To split each of these cells back. Okay. So the one where it's Shift M, I have to be in command mode in the Jupyter Notebook. So I have to have this blue bar on the side. Then I do Shift M to combine. And then to split them, I have to be inside the cell in edit mode. So I need this green bar, and I'll see my cursor inside there. And then I do Shift minus to, and then I'll split the cell at my cursor. Okay. Okay. All right. So, okay, so here's a longer question. So it's only the k-means method that allows us to calculate inertia. How do you handle treat instances where we cannot use the RAND score to evaluate performance when we do not have a canonical set of clusters to compare with? Yeah. So basically, when you don't have ground truth, it's true you can't use RAND score. We can measure the inertia of clustering, since inertia is the sum of distances from each point to the centroid. We expect near zero numbers. We're just trying a probabilistic approach to clustering, like a Gaussian mixture model. Yeah, so in the Python data science handbook, in that example, where they're clustering, they're using a Gaussian mixture model. And I think that's, a great example. Based off of this plot, it looks like it's performing better yeah, than the clustering that I did with agglomerative clustering. So that may be a good choice. You're right. If you don't have the ground truth, you cannot use this RAND score, right, in order to assess your clustering, but you can still use the silhouette coefficient, right? So k-means is nice because you can get this kind of inertia, and then use inertia. So the lower inertia, the better the clustering. You can use inertia to assess your clustering. But for any of these clustering algorithms, you can use the silhouette coefficient. So I would recommend using silhouette coefficient, right? If you know, in situations where you can't, you can't get inertia easily, right? Or basically inertia is going to be based off of that within the cluster center, but the cluster centers will still have, you'll still have like a cluster mean, right? And so you can still calculate that within sum of squares, right? That for each cluster. So you can still calculate it, but if scikit-learn doesn't provide it for other estimators, that's that's fine. You can still use the silhouette coefficient. Okay? So the silhouette coefficient is kind of a tool you can use always, and so it's a good choice. You don't need to know ground truth, unlike the RAND score that you mentioned, right? As for using kind of a probabilistic approach like a Gaussian mixture model, I think that's a great choice for clustering. Okay. All right. Okay. So Helena, I'm just showing kind of ways that we could maybe obtain this data set, and then if you're kind of still having a problem in a second, let me maybe continue what I was talking about. If you're still having a problem, certainly you can share your screen, but give me one more second to kind of explain what we're going to do, right? So the digits data set, the reason why I, kind of loaded this in or did it this way is just to mention is if you have Jupyter Lab open, you can open up a CSV file in Jupyter Lab to view it, right? So here in this kind of classic Jupyter Notebook interface, we're not going to be able to really, I think, interact with this digits of .csv, but I'll want to show you how this looks in Jupyter Lab. Okay, so just kind of bear with me. I want to go somewhere with this, right? So here I'm going to scroll down all the way to the bottom of this notebook. All right, so here are the exercises. And now I'm going to actually grab the code that I had before, which I think I still have in my, yeah, I still do. Okay, so here I'm just going to kind of download this digits.csv. Go here. Okay, so actually I called it digit.csv. That's just what I called it. Okay, and then I can double click it to open it in Jupyter Lab. All right. So here, this is what it looks like, right? And then this CSV viewer inside of Jupyter Lab is pretty nice. I can kind of scroll through this without any kind of problems. Maybe it's not necessarily a very interesting data set, okay? But I can kind of scroll through this without any problems. Okay? All right, so now I'm going back to what we were just working on. All right, what we're going to do instead of working with kind of this local file is we're going to read it in using pandas. We already have some information here. So for example, we know that we know how many rows and columns there are, and the other thing that we should kind of know is that the data frame should not include the final column, okay? Because the final column is going to be the labels, and we only want to load the features, okay? So what are we going to do? We're going to, we've already done the required imports, which is here. Okay, so import NumPy, import pandas, all right? And then down here, what I'm going to do is I'm going to do, so we're supposed to call it digits according to the instructions. Okay, so digits equals PD, read CSV. And we're going to then inside of quotes, or sorry, we already have the URL here as the string. Okay, so we're just going to use that. All right, so the first part of this is we're just reading in this digits as a data frame. Okay, and we'll want to drop that last column. Okay, so we can use this useCalls argument. All right, so to do that, so here use calls. So we can do list like or callable or something like that to return only a subset of columns. All right. So we know how many columns we're going to have. Actually, let me kind of delete some of this so we can look at what we're working on, and then here. So we know we have 64 columns. Right? And so if I have use calls, and I'm going to then maybe use a range object. And so the range object is going to go up to, but not including 64, right? So it's going to start, so that would be all of the columns, but we want to, not have one of the columns, okay? So let's try this, all right? So what we've done is we've read just the features, not the labels. Okay, so this is kind of like a quick way of obtaining just the data. Okay. Another way that I can do this is I can read in the whole thing. All right, so I'm going to call this data frame. I'm going to read in the whole thing. And then I'm going to drop 64, but I have to specify, so let's just, I think I have to do, let's maybe take a look. Let's do df head. All right. So the other thing that I have to do here, looking at this, is I have to specify that there's no header. Okay, so header equals false. Oops, oh, actually, maybe header equals none. Yeah, that's correct. Okay, so it has to be header equals none. And then I can look at the head of this. All right, and now I have my column names 64. All right, so I'm going to do now drop 64, and I have to say axis equals 1 in order to drop this number 64. Okay, and so then what I'll do is I'll assign it to digits. Okay, and then I can kind of confirm here by looking at the shape of digits that, yeah, so I'll have now 64 columns. Actually, so here also I should have 64 columns because it looks like the data frame is 64 attributes and then the label. Okay. All right. So that looks good. And then if I want the labels, what I can do is maybe kind of use 64. So I still have this column name. And then now I'm going to have my labels. Right, so the labels are going to have, if I look at the unique values, the labels are going to range between 0 and 9. All right, so I think, yeah, so here it says, instead save the final column in appended series named labels. So what we want to do is actually exactly what I put there here. So, okay, so df equals read underscore CSV, then drop that 64th, or sorry, the one indexed by 64, so it's actually the 65th column, and then take that 65th column, the one indexed by 64, and then assign it to labels. Okay, so all this works really well. So I'll go ahead and copy this and paste it into the chat. Okay. Let's see, in the chat, all right, so Helena, if you could, try to just run the code.
Okay. Well, what I have is what you just did, even though I didn't do it that way. That's what I was going to share, but not see that it's correct. But what I like what you did, you explained in detail where it took me to when I was trying to get this information because I could not unload. It took me to GitHub and Python machine learning, where it had a lot of the information there, so I copied and pasted it. But what you just did, the area I didn't put, but the labels, I print labels and it came out correctly the same. And I have the same numbers that you have, pretty much exactly, except you had dropped the number. So I didn't drop that number, but that's why I want you to share so you could see. But what I have is pretty much what you have. But I like what you did, much clearer. It makes it much easier to understand. Thank you.
Yeah, thanks so much. All right, so so this is what I'd consider, the correct answer, and then also what I have. Oh, and you don't have to worry about this at all, but I have some kind of test code. So the TAs will have this kind of test code. You don't have to worry about it. Basically, what it's going to be is that when I run this test code, if I don't get an error, means that we've done everything correctly. Okay. So were you saying something else?
No, I didn't. Let me just unmute myself.
Okay. All right. So the shape is correct, right? And then, the values here, some, I know that this is correct. So when all of these assert statements can run without raising an assertion error, right? We know we've done it correctly. So the TAs have this code to kind of double check what we've done. All right. Okay, so here, what we're going to do is we're going to kind of pre-process the digits data set. All right, and for that, we're going to use here the scale function from the pre-processing module of scikit-learn. Right? Okay. So what we want, though, is we want the result to be a pandas data frame that's been scaled or standardized, right? So we're going to have a mean of each column. The mean is going to be close to 0, and the standard deviation is going to be close to 1. All right, so that's the final result. Okay. All right. So let's first maybe copy this here, scikit-learn preprocessing.scale. All right, and I'm going to say import, or actually, sorry, from scikit-learn preprocessing import scale. All right. Okay. And then I'm going to, maybe call it scaled, and I'll do scale digits. okay? And then I'll have, maybe I'll call it scaled df, and then pass it to pandas dot data frame. All right. And so I'm going to pass the scaled thing to pandas data frame. So let's take a look at scaled. Okay, so it's a NumPy array. All right, so our digits data frame is, of course, a data frame. All right, but what the scale function, what it does is it returns things as a NumPy array. Right? So if I look at the type here of this, what it's going to be is a NumPy array, but I want it as a data frame. So that's why I have this additional step of taking this NumPy array and turning it into a data frame. All right. So now if I look at scaled df, all right, here's my data frame. Or actually, to save a little bit of space, I can look at the first 5 rows. All right. Okay. So that's it actually for this second exercise. It's pretty simple, or I think it's fairly simple. All right. So I'm going to combine all the code here and then paste it in the chat so that you can, you can try it yourself. And then I also have some code with some assert statements. Okay. So what this is going to do is it's going to say, all right, so the values, that's going to be how I get out a NumPy array. So here I'm going to have to change this to be scale df, because that's the final thing that I called. So scale df instead of digits, because I renamed it because I wanted to look at each of these things kind of individually. All right. So because I renamed everything, I can compare now digits and scaled. Okay. So here's the original, and here's the scaled version. Okay. All right, and now here I have some asserts. So again, the TAs have this. You don't have to worry about having this. This is just something that will check that, the values, okay, here, okay, that, these conditions are kind of met, right? So mean of close to 0, standard deviation of close to 1, right? So here, first of all, the mean close to 0, right? And so if that runs without errors, that means we've done this part correctly, all right? Let's maybe try this. So we'll look at, here, scale df mean, okay? So these means are close to 0, right? And so we can use something like np dot is close, right, on this. So this is going to give me back a bunch of means. So I might want to do np.all, right, to make sure that that I want kind of all of these things to be close to 0. Okay? So let's try that. Okay, so it comes back as true. All right. And then the other thing that we wanted was for scaled df std. So this is the standard deviation. Okay, looks like this first one, the standard deviation is not 1, because in that column all of the values are 0. Okay, so maybe what I can do is I can just kind of skip that first column, right? So I'll do it after. So let's start at 1 and then go to the end. right? And then I'll want to say something similar to what I did here. Pretty much the exact same thing. All right, so np.all, np.isClose, right? And then I'll want the standard deviation to be close to 0. Sorry, close to 1. Okay, so here it's showing up as false, and I think the reason for that is because I probably have more of these examples where I have, you know, columns which are just filled with zeros, right? And so their standard deviation is going to be 0. It's not going to be 1. But essentially, wherever we have some kind of values, we don't have just an empty column. We're going to have a mean of 0 or close to 0 and a standard deviation of 1. So that's what I'm showing here. So STD gives us the standard deviation. You can see that, you know, most of these are close to 1, just like how the means are going to be close to 0. So these are, you know, really, really very, very, very small numbers. And so, you know, all of them are close to 0. All right, so this is just kind of checking how I, you know, ways that I can show that, you know, these things are working. So the scaling is working. Okay. All right. So what I heard is that we can go until 1:30, and you know that works for me. So I'm going to keep going. Okay. There's one other thing that I maybe would want to do, just kind of for fun, is to show this STD. Right. I'll want to do np.isClose to 1 for let's call it S, for S in scale.std. All right. And so I'm going to get out, you know, a bunch of kind of trues and falses. All right. Okay. np.isClose scaled std. So I'm getting actually a bunch of falses, a lot more falses than I thought. Maybe I'm not so sure why, actually now, because when I look at, okay, maybe it's because, you know, kind of the tolerance isn't high enough. Okay. So isClose has this, you know, absolute tolerance parameter. So I might have to fiddle with this to get it to turn out right. But one way that I can look at all of these values is to use this kind of list comprehension and iterate over it. Right? So maybe let's try this. Right? Changing this ATOL. I'll see if I can. All right, so here I adjusted this ATOL and now I'm getting trues. All right, so looks like wherever it's false, that's going to be a column that has all zeros. Okay. All right, and so what I can do is I can maybe try to, you know, use this, kind of use the inverse of this to pull out kind of my standard deviations. Okay, so here these are going to be the standard deviations that are not, that actually work for this. So let me see if I do something like this. So if I do this, these are going to, oh, so these are going to be the ones, yeah, these are going to be the ones actually that are close to 1. So the majority of those are, right? If I look at the shape of this, Well, it's 61 out of 64. So 3 of these columns are filled with all zeros. Okay. All right, so this I was just doing for fun, just to kind of explore a little bit. All right, but the code in order to do this I already shared. It's just those 3 lines, the latest thing that I pasted into the chat. And then what I'll also do afterwards is I'll also put this in Slack. I know that you won't have access to the chat after we finish. Right? Okay, so next up, what we're going to do is we're going to kind of examine how many clusters that we might need for k-means clustering using the elbow method and the silhouette coefficient. All right, so here there are lots of instructions. All right, so it says run the k-means algorithm on the digits data set 24 times. In the first run, set the number of clusters to 2, right? It doesn't make sense to have, just one cluster. So we'll start at 2, and then we'll go on up to 25. All right, so in each run, collect the sum of square distances. So this is the inertia. All right, so save these into a list called SSDS. And then we're going to create an elbow plot and then look for that inflection point. Okay. So the second part of it, we're going to use the silhouette score function from this metrics module. And then I think this is a mistake. It's no longer in the submodule called cluster. It's just in the metrics module. So if you ran into a problem with that, I apologize. This is just outdated. Okay, but the TAs have correct answer code. Okay, all right. And by the code that I'm typing right now, it's probably going to be different than what the TAs have, just because I'm kind of doing this, slight variations. What I'm doing may differ a little bit because there are probably multiple ways to do the same thing. Okay, all right, but let's get started with this one here. Okay, so we have some of these things I think already imported from before. Let me double check that. Okay, so I've got silhouette score already imported. This is if you're running everything here. Maybe what I'll do is I'll actually use this here. So I have to get rid of cluster because with cluster with cluster it also works, looks like. Okay. All right, so that's fine. I think it's the same thing. It's just available from metrics and then also from cluster. And then for the inertia for the elbow plot, we don't have to import anything kind of like special for that because it's going to be included with k-means. Okay, but we do have to import k-means. So I'm just going to do the imports just to kind of include those, right? So what we can do is we can start off with a list, and so it's going to be an empty list. Okay, this is where we're going to put our sum of square distances. Okay, so these inertias. All right, and then what we're supposed to do is we're supposed to say for I in range 2, 26. Well, it's so 25. It's supposed to go up to 25, but the intention is that it's going to be including 25. So here I have to put 26. All right. And so the next thing that what we're going to do is we're going to do SSDS dot append. Okay. And we're going to include actually a lot of things here. So we're going to do k-means. We're going to instantiate it. We're going to do n clusters. So this is k. And we're going to do n clusters, here we're calling it I. Maybe actually to make it a little bit more easy to understand, we'll call this k, right? All right. And then, you know, we can provide some kind of random state. I think that might be good so that we can have the same result, right? So random state equals 0. And then we're also going to do fit to digits. So that's what we have before. Well, actually, you know what I call it is scaled df. And so scaled df. And then I want the inertia. Okay, so inertia has this underscore at the end. This underscore, what it means is it's something that's obtained after fitting. That's kind of a naming convention in scikit-learn, that after we fit, we're going to have new attributes which are followed by an underscore. Okay, so this code right here, this is, you know, the intent here is to collect all of these, you know, sum of squared distances. Okay. So here, while that's running, it's taking a little while. While it's running, what we can do is we can start thinking about the plot code. All right. So what I want to do is maybe you know, set this up to be plt.plot. So we have this, this import was from earlier in the exercise, actually from the very top of the exercises, was here, import matplotlib, the pyplot as plt. Okay, so I'll do plt.plot, and then I'm going to use a range object, and then go from, you know, the same range. So maybe I should have created a variable, but that's okay. And so those are going to be all my key values. Okay? And then I'm going to put in my list here. So I'm going to plot that. Then I should have a title. Okay. So maybe I'll call it, you know, elbow plot. I'm going to say, right, so K values, maybe something like sum of squared distances versus K. All right, so that's my title. And then I guess it's a little bit redundant because now I'm going to provide X label. So the X label is going to be K. And then the Y label is going to be sum of squared distances. Okay. All right, so this ran. I'm going to just show you what this list looks like. Okay, so it's a bunch of inertia values. These actual numbers don't really mean anything to us, and that's fine. All right, but we're going to plot them out now, and this is our elbow plot. All right. So is there a clear inflection point here? I would say there isn't. Okay, it looks more like a straight line rather than, you know, rather than an elbow. So I would say here it might be difficult to use the elbow method to say, you know, where is there a clear inflection point. Okay. So the next thing that we might do is to use the silhouette coefficient as another option, as an alternative to this elbow method. Okay, but really quick, when I look at this code, I say it's pretty much asking to be rewritten as a list comprehension. All right, so I'm going to do that really quick. So we're going to, it's going to simplify the code. I think it's also going to be easier to understand. All right, so we're going to be pulling out these inertias, and then we're going to say, you know, for K in range this, right? Then we don't need this part. And we're going to have this be SSDS, all right? So you know, I guess one thing you could say is, okay, so this fits on a single line of code. Yeah, maybe that's good. I don't think that's maybe, that shouldn't be a goal. And what I can do to maybe make this a little bit easier to understand is break it up onto multiple lines, all right? But you know, these pieces of code, so here this 115 and this 115, they're synonymous. Okay, so we would only do one of these. All right. And what I'm going to do, since I like list comprehensions better, right, I'm going to comment this out before I combine these cells and say, so this is going to be, you know, the result for the first part of exercise 3. All right, so paste this into the chat as well, so you have access to it, just so, you know, you can kind of follow along. So here's the exact code that I have here. All right. Okay, so the next thing that what we'll want to do is we'll want to use, you know, this kind of silhouette coefficient as an alternate method, because we can't really maybe rely on this elbow method, because the elbow method doesn't really give us a clear inflection point. So where would we, you know, what value would we pick? I think it's very hard to say. Okay, so what we're going to do is we're going to, you know, use a very similar approach, because first I'm going to kind of show you how it would look like as using a for loop. So we're going to, when we're using a for loop, we first initialize a list, okay, and then we're going to actually have the same exact setup. So we're going to say for I in range 2 through 26, okay. Then we're going to kind of do SCS dot append. So here, this is going to be like our silhouette coefficients. That's the idea of the variable. Okay. And so what we're going to do is we're going to use our silhouette score function, and we're going to have to pass in our you know, our scale df. Okay, and then we're going to have to have k-means, right? And so for k-means, we're going to have to instantiate it, right, with a certain number of clusters. Okay, so the n clusters will be I in this case. All right, and then we're also going to have to, you know, provide some kind of random state so that we can have comparable results. All right, and we're going to want to fit it to our scale df, okay, and then access the labels, so the cluster labels. All right, and so this is, you know, a bunch of code all on one line. You know, it probably is going to be better to break it up into multiple lines, but kind of this is the way that I decided to do it. All right, all on one line, and I can put line breaks in. So wherever I want, for example, here with silhouette score, I can put some line breaks in here. All right, to maybe make it a little bit easier to read. Okay. All right, so this is the code that we're going to use to collect all of our silhouette coefficients. All right, and maybe what I'll do right away is I'll take this code immediately and just redo it as a list comprehension. All right, so for the list comprehension, I'll want, you know, square brackets, and then I'll want the thing that I'm going to get, which is going to be these silhouette scores. And then I'm going to want the iteration logic. Okay. Right. So again, these two cells are going to be synonymous, but I prefer doing it with, you know, a list comprehension. That's just maybe like a personal preference. So I'll do scaled df here for I in range 2 up to but not including 26. All right. Okay. So these two, code blocks, they're the same. So I'm going to comment out one of them. And I'm going to get this running because I think it may run for a little while. While it's running, I'm going to create my plot. So what is a name error? So K means, of course, because I was typing this out by hand. I forgot that the M is going to be capitalized. Okay. All right, so let's try it again. All right, so it's running. The fact that it's running means that it's working. It's just going to take a little while. All right, so we're going to do plt.plot again. And so we're going to do this range again. I really should have assigned this to a variable. It would have been easier. And then SCS is, those are going to be the values that we're going to be plotting on the x-axis, okay? And so then I'm going to do plt.title. And so this is going to be the silhouette coefficient plot. All right, that's going to be the title. And then the plt dot x label is going to be, let's maybe call it, let's call it K again. I think that's fine. So the number of clusters is K. And then the Y label is going to be, I'm not typing that again. I'm going to copy it. Silhouette coefficient. All right. So it looks like it's done. And now we have our silhouette, coefficient plot. So this is useful. We see that there's kind of like a clear peak. All right. And again, the result, I think you'll get the same exact result, but for that you have to set the random state to be the same number that I did. Okay. So if you run the same code, I think you'll have the same result, right? So there's kind of like a clear peak here, right? And we might want to know what is that peak, okay? And so we might want to, so this SCS, it's going to be like a list, right? Okay. And for this, what I might want to do in order to say which of these is going to be the highest, I can use this kind of index max function or method, and it's going to tell me that the highest, or the index of the highest, is going to be 16. All right, but that doesn't actually automatically correspond to what we're working with, right? Because what we would have to do is, kind of create a data frame, all right, where we have our here these silhouette coefficients, and then our range object here. Okay, so what I'm going to do is I'm going to do pd.dataframe. Right, and I'm going to use a dictionary here. So I'm going to say, K is going to be this range 2 through 26. Again, I should have definitely created a variable for this. I'm typing that a lot. And then our scores is going to be this SCS, okay? So here's our data frame. All right. Okay. And then we know that the index of the highest, so it's right here, right, is 16, right? And that corresponds to a K of 18. So what I would do from that is I would do, first of all, let's assign this to a data frame. So let's call this, I'm going to call it silhouette coefficient DF. All right. And then in our silhouette coefficient DF, we're going to want to get out the row that corresponds to the highest. So this is index of the max. So I'm going to do SC DF, and I'm going to get out the scores column, and I want to do index max. Okay. All right. So this is the index of the max. We've got the highest score, which is 0.16 and a half, let's say, right? 0.164. All right. And the optimal K is then 18 clusters. Okay, so that's what we're looking at here. All right. So with this digits data set, we've got a clear kind of winner with the silhouette coefficient, but not so much right, with the elbow plot. All right. Now, so I see someone here is mentioning some things. Okay, so let's see. Argmax will also work, right? For sure, right? And then if we want to do that, you know, we can also access it as a NumPy function, right? So here, return the indices of the maximum values across an axis, right? So if I wanted to do here, actually, you know what? I think, will it work on a list? Yeah, it'll work on a list, actually. So I wouldn't even have to turn it into a series. Yeah. So that's probably going to be a little bit more convenient. So another thing that I could have done, I mean, I'm glad I created this data frame, right? But another thing that I could have done is assign my range object to a list and then indexed it using this IDX max, right? Or this NP arg max SCS, right? Okay, you know what? I've talked about this enough that I think I really should do this. So I'm going to call this K range. All right, and I'm going to maybe what I'll have it be is I'll have it be a list because I'll actually want to use that later. Okay, so here I'm going to have K range, and wherever I say this range, I'm going to just do K range. Okay, so that's generally speaking, that's easier to type. And I think it's just going to be better. All right, so now I'm just kind of replacing it in all of these cases. All right, and so, you know, this is still going to work as long as I run it. Let me run it. I think I did run it, right? Yeah, I did. Okay, so here I've got my data frame. Now I've got my K range. So what I could have done is done K range. All right, and just gotten out this answer. All right, so I think that's probably, this is going to be the easiest way to do it. All right, so let me put this code together. Actually, let's actually put all of this code together. So I'm gonna kind of copy it from the very beginning, provide all of the code all together, everything to make the silhouette plot, to make this data frame, and then also just to find out what's the optimal number of K. Okay. So it's going to be a lot of code, but that's okay. So this is more of like a complex exercise. It's a lot harder than the others, right? All right, so I'm pasting that into the chat. So you can copy and paste that. That's the entire answer to exercise 3. Okay, so there's another question here. Certain algorithms have specific features for outlier handling. The algorithm click goes a step further, it eliminates subspaces with low coverage. Okay, the algorithm ORCLUS produces a partition plus a set of outliers. Do you recommend using this if the outlier is the commodity of trade? All right. In other words, in the field of medical diagnostics or computer immunology. Okay, so yeah, these algorithms can be great, but sometimes, the outliers may be what we're most interested in. So yeah, so I think, they can be great choices, right? Including in, the fields like medical diagnostics, let's say computational immunology, for sure. Okay. All right, so we're almost at 1:30. Okay, so I'm not sure if we should get started on number 4. But basically what it's going to be is it's going to, we're going to get out this kind of adjusted rand index or ARI score, right? Or so the adjusted rand score or adjusted rand index, right? And we're going to kind of print out the score. Actually, you know what? I think we can try to squeeze this one in. Okay. All right. So because basically, what's provided here is this adjusted rand score. Okay. And then we already have our labels here. So all we have to do is so we should have actually. So I've never actually kind of assigned that k-means to. So let's do model equals k-means. We're going to try to squeeze this in before we run out of time. So model k-means, we're going to have a number of clusters. Let's go with 18. That was like the optimal of what we saw from the silhouette coefficient. So let's go with that. And then I'm going to do random state is 0. Then I'm going to do dot fit. Okay, so we're going to do fit, and we're going to fit to the scaled data frame. Okay, so there's my model. And then my score is going to be this adjusted rand index score, where first I pass in the true labels. And so that I have further up. And then for my model, I'm going to access the labels. Okay. All right, so with this, I think that's actually it for this exercise 4. Okay. Oh, here it's saying actually to use a different random state. Yes. So the reason to use that random state versus another one is so that the assert code that I gave to the TAs, so that it works, right? So here, so you'll have assert code like this that the TAs have, and they'll have, I have to assign it to score. Okay, and then if this runs without, so it looks like there's some kind of, assert, one of the assert statements returned an error. So if this runs without a problem, then, you'll have, you're kind of sure that it's correct. Let's take a look at score. How close is it? Oof. So it's kind of pretty, because yeah, I think it's supposed to, you're supposed to do 10 clusters. That's what it is.
Yeah.
Yeah. Okay, so now it runs without a problem. All right. Okay, great. So that's all the time that we have. So we got up to, we did exercises 1 through 4. There's still exercise 5, 6, and 7, which you can work on during office hours. And so those are going to be a little bit more involved. Okay, so if you have trouble with those, don't worry. What we've covered so far is quite a lot, right? And, I hope at this point you feel kind of more comfortable with clustering, how to set it up, right? And then methods for evaluating clustering. So we've covered, elbow plot. We've also covered, silhouette coefficient. Yeah. Okay. So let's see. So I'm looking here. There's a question. So could we plot Q4? So
I think I recall that. I think we the survey is more relevant, and
sure.
so yeah, I'll take them through that.
Okay, sure. So here we wouldn't plot it. It's just an assessment of the entire model. We could do it for every single cluster. So we could plot it. Yeah, we could for sure. Right. Okay. All right. So looks like this module 8, presentation 2. So looks like it's coming up next week, Thursday, 11 to noon. All right. That looks really great. I met Jeff Leake when I was at Johns Hopkins, so that's going to be an amazing presentation, I'm sure. Any questions?
Okay, so any further questions for Martin? Okay, so if you don't have any further questions, I think at the peak I saw about 51 of you signing in to this presentation, and then just about maybe 1 minute ago, all 50 of you were here. So that tells me that you found this presentation very informative, and then I believe you learned a lot out of it. So Martin, we thank you for a very excellent presentation over the past 2 days, and then I'm sure when we are doing this again, and we call you, you will willingly come. Hopefully at that time, you will not be engaged yourself in another program, because I see that you keep on having degrees here, masters and certificates all over the place. So hopefully at that time, you will be available and then you will join us again. So again, all of you, show your appreciation by waving to Martin for an excellent 2 days of presentation. Put your cameras on so we can see you. Don't hide yourself. You are now a family. All right. So as Martin said, the next research presentation is next week. And then as you can see from the title, especially those of you who are in genetics, genomics, I think is going to be very interesting. What you can learn about human gene expression when making 70,000 RNA sequence samples easy to use. So I hope all of you will be here for that presentation. There will be TA sessions on Saturday from 9 a.m. to 10 a.m. So check Slack for the link to that section, and then also Sunday from 5 p.m. to 6 p.m. Other than that, the next module, other than next week's presentation, will be in 2 weeks. That will be on classification model. So thank you all for coming, and then have a great weekend.
Thank you.
Thanks so much, everyone. Bye.
All right.
Thanks a lot.